Hello, this is Module 4.1, which discusses MOSFET fundamentals. So the coverage is Introduction to MOSFETs, NMOS versus PMOS, transistors, the MOSFET structure, and basic MOSFET operation. And also we will introduce new terms special for MOSFETs. So for this module, the main transistor that we're going to use is the metal oxide semiconductor field effect transistor, or MOSFET. So the basic application or the basic operation of this transistor is that an electric field is applied normal to the surface of the semiconductor. So how do we produce that electric field? So we apply a voltage over an overlying conductor, which is, for here, it's the gate here. And because of this, we can modulate the conductance of the semiconductor. So how do we produce current in this type of transistor? So if you introduce a voltage in the gate here, there will be a conduction path from source to drain depending on the value of the gate. And if you introduce voltage across the drain and source, there will be drift current flowing between these two contacts. This operation will be discussed in detail later. So what are the two types of MOSFETs? So there's an NMOS, or the N-channel MOSFET, and there's a PMOS, which is the P-channel MOSFET. So the NMOS uses electrons as charge carriers. They're faster and smaller, and they have lower on resistance. On the other hand, the PMOS uses holes as charge carriers. They have higher off resistance, so that means it has low off leakage and easier to control. So what are the parts of a MOSFET? So for both NMOS and PMOS, they have a substrate or a bulk. So for NMOS, a p-type substrate is used, shown here. So this is a p-type semiconductor, or for our application, a p-type silicon. And for a PMOS, an n-type semiconductor is used as its bulk, or for this application, or for this introductory course, we're going to use n-type silicon. So in order to create the two terminals of the MOSFET, so we will use heavily doped semiconductors. So for an NMOS, because the NMOS transistor uses electrons as their charge carriers, we will dope it with n-type silicon, so shown here. And because the PMOS uses holes as their majority carriers, therefore we're going to use p-type semiconductor as shown here. And then there is an oxide that will be deposited on top of the transistor between the source and drain, which is shown here. So usually for real MOSFETs, silicon dioxide is used for this. And then a metal, shown here, which is usually heavily doped polysilicon, will be deposited on top of the oxide, and this is where the gate terminal is located. So this is the basic structure of a MOSFET, and we can label them as shown here. So the gate is in the middle, and it is here in the connected to the metal, and the source and drain are connected to the heavily doped terminals here and here, and there's a bulk terminal which is connected in the substrate. So for this introductory course, the bulk will be assumed to be connected to the source always, and will be not shown in calculations. So in 3D, this is what it looks like. So there's a substrate, the source, the drain, and this is the gate. So this is the oxide, and these this one and this one are metals, or vias as we call it, just for where the wires are to be connected. So the distance between the terminals is the length, and this is the width. So this is a real MOSFET used in Intel before. So this is a 35 nanometer MOS transistor. So it has a length of 35 nanometers. So think of this, the distance between the source and drain is 35 nanometers. So now there are two types of MOSFETs. So there is the enhancement mode and the depletion mode. So for an enhancement mode MOSFET, the conduction between the source and drain is enhanced by applying a gate voltage. This means that if the gate is 0 or grounded, there will be no current path between source and drain, shown here. And then there's a depletion mode type of MOSFET. So a gate voltage must be applied to cut conduction between source and drain. So this is the default on MOSFET. So that means if the gate is 0 or grounded, there is a path between source and drain. Okay? So for this course, we will only consider enhancement type MOSFETs. So how does a MOSFET operate? So in order for us to understand this, let's consider an NMOS and a PMOS where the source and bulk are connected. So that means the voltage across the bulk and source is 0. So they're shorted. So shorting the source terminal and applying a negative voltage for a PMOS and a positive voltage in the NMOS to the gate, to their respective gates, shown here. So what will happen? So because of the applied voltage, the majority carriers of the substrate are expelled from the surface of the gate oxide, and more minority carriers are attracted to the surface of the gate oxide. So what does that mean? So for example, for the NMOS, if we introduce a positive voltage across the gate, the holes in the surface will move away from the oxide because there is a positive voltage here. And also, the minority carriers, the electrons shown here, will move towards the surface because there's a positive charge. So same concept here. Because we introduce a negative voltage here in the gate, that means that the majority carriers of this n-type substrate will move away from the surface, and the minority carriers, which are the holes, will move towards the surface. So that means that because of this, a current path will be created. So now it depends on the magnitude of the gate voltage on how wide this path would be, and how wide this path will define the conductance of this of the path between the source and drain. So this is called the path created is called a channel or an inversion layer. Okay. So that means we can define the threshold voltage from that idea. So the basic idea is the threshold voltage is the gate source voltage, so the voltage across the gate and source that causes the concentration of electrons for NMOS, because electrons are the electrons are the components of the channel, and for PMOS it's holes, immediately under the gate oxide to be equal to the concentration of holes or electrons, effectively creating a channel, shown here. So if the MOSFET gate source voltage reach this threshold voltage, so let's name it THN for NMOS and THP for PMOS, current can flow from source to drain. So the threshold voltage of an NMOS is positive because we need the positive voltage in the gate to create the channel, and for the PMOS it must be negative in order to create a positive a whole channel. Okay, so that means this threshold voltage is defined to be the voltage needed. So if the gate voltage is less than the threshold voltage, there will be no channel and there will be no path between source and drain. So now, if we reach this threshold voltage, so for an NMOS, let's name it VTHN, and for PMOS, it's VTHP. So that means if we introduce a voltage across the drain and source, shown here, that means that there will be an electron flow from the source to the drain for an NMOS, and there will be a whole current flow from the source to the drain for a PMOS, shown here. Take note of the polarities shown here. So for an NMOS, you introduce a positive voltage in the drain, and for a PMOS, you introduce a negative voltage to the drain. So electron flow for an NMOS from the source to the drain by a drift, and for PMOS, it holds flow from the source to the drain. So that means if we consider the definition of current, so that shows here that the current flow, because the electrons are moving from source to drain, therefore the current flow is from drain to source. And for the PMOS, it's from source to drain because the holes are moving from source to drain. So now, this current is dependent on the value of the gate source voltages and the drain source voltages. Now, because as you can see here, in the drain side, if we increase the voltage across the drain, because the substrate and the drain is a reverse biased PN junction, that means that the depletion region here will widen. Same concept here, because you are biasing this PN junction in its reverse mode, so you increase the depletion width here in this terminal. So that means at a certain value of VDS, or the drain source voltage, the channel will pinch off at the drain side, because instead of having electrons here, this will become a depletion region. And also, instead of having holes here, this will become a depletion region. So there will come a time that the channel will pinch off when this happens. So now, because we know that will happen, we can now define a certain voltage to be the saturation voltage. So the saturation voltage, let's say VD sat, is defined as the minimum drain source voltage that causes the channel of the transistor to pinch off in the drain side due to widening depletion region of the drain bulk junction. So that means if the MOSFET reach the saturation voltage, it means that you bias the VDS of the NMOS or the PMOS to assert the VD sat, further increases in the drain source voltage. So if we increase this further, we'll instead of having increased current due to higher electric field here, because the channel is pinching off, there is a bottleneck here. So further increases in the drain source voltage will have little to no increase in the drain current. So the drain current is the current from source to drain due to the increase in voltage compensating for worsening channel pinch off. So for introductory courses, it is approximately equal to VGS minus VTH. So that's it for this module. So the summary, I hope that you have learned that first off, the MOSFET structure is comprised of a substrate, source and drain terminals, an oxide, and metal for the gate terminal. So the NMOS has electrons as charge carriers, while PMOS has holes as charge carriers. So there are two types of MOSFETs, the enhancement mode and the depletion mode. And for this course, we will consider the enhancement mode MOSFETs, and also um, the threshold voltage is also introduced here. So just to recap, the threshold voltage is the minimum gate source voltage needed for current to flow from source to drain. And when the transistor reaches the threshold voltage, so a channel or an inversion layer is created. And then also another concept introduced is the saturation voltage, VDSAT, which is the minimum drain source voltage needed that causes uh, the channel to pinch off in the drain side due to widening depletion region. Further increases in VDS from VDSAT does little to no change in drain current. Yeah.